Hello, welcome back. We are going to continue our discussion on the mole. If you remember, we were talking about the mole as being a very special number in chemistry, and it is the number of particles that is going to give you a mass equal to the atomic mass for that particular element or the formula mass for a particular compound, but it is measured in the units of grams. So let's continue to talk a little bit about the mole, and specifically we're going to be looking at the mole in chemical reactions. So we're going to be talking about how things react, in what ratio, and specifically in what molar ratio. So we're going to be looking at the coefficients in the balanced equation and how those coefficients tell us in what ratio the different reactants are going to react. A balanced equation, remember we talked about that in the previous video, we're going to continue to balance equations today, tell us the number of reactants and products that are going to basically react, be produced or be consumed in a reaction, and they have to be equal on both sides, meaning the number of each element have to be the same on both sides. Otherwise we are somehow losing something or gaining something mysteriously. We have to conserve mass, in other words. So typically when we balance the chemical equation we think in terms of individual particles, but remember we mentioned that we can't count, we can't see individual particles, so we often talk in terms of moles, a much larger quantity in chemistry. And remember that mole is just a number, okay? So we talk about larger quantities in chemistry instead of just an individual particle. So in this activity we are going to look at different ways to explore a chemical reaction and how we interpret the numbers in a chemical reaction. Model 1. We have a chemical reaction here in the box, and looking at that chemical reaction we are asked what are the coefficients for each of the following substances in the reaction. Coefficients are the big numbers. If there's a 1, we don't write it, but there would be a 1 right here. So the coefficient for nitrogen is 1, the coefficient for hydrogen is 3, and the coefficient for ammonia is 2. Okay? Draw particle models below to illustrate the reaction in model 1. So nitrogen, N2, it's diatomic, means you have an atom of nitrogen bonded to another atom of nitrogen. There's just one of those. We have 3 hydrogen molecules. Hydrogen bonded to another one, and that is occurring 3 times for us. And then we have 2 ammonia molecules. That is nitrogen bonded with 3 hydrogens, and there are 2 of those. Okay? Consider each situation below as it relates to the reaction in Model 1. Calculate the amount of reactants consumed and products made. And record the ratio of N2 to H2 to NH3. Reduce the ratio to the lowest whole numbers possible. So let me just make a couple comments here. In this reaction, you have to have the same number of each element on both sides. Here is our reaction arrow. All right. Basically, you've got a molecule of nitrogen, and that molecule of nitrogen is going to react with 3 molecules of hydrogen. These bonds in the reactants are going to be broken apart. If there's enough energy, they're going to be broken apart when these particles all collide. When they all collide, energy is going to break these bonds apart. Now they are free and mobile in order to rearrange themselves and form new bonds. What new bonds do they form? They form our 2 ammonia molecules over here. So when these bonds get broken, these 3, for example, hydrogens are going to find a nitrogen, bond with them. These 3 hydrogens are going to bond with the other one. Do we have the same number of each element on both sides? Yes, we do. This is balance for us. How does it occur? These 2 nitrogens split and are part of each individual molecule over here. Here's a nitrogen, here's a nitrogen. So we got 2 nitrogens on both sides. 2 here that were in the original molecule, and there's one in each of the ammonia molecules, but there are 2 molecules of ammonia. The 6 hydrogens here, there are 2 in each of the 3 molecules. Now there are 3 in each of the 2 molecules, but there's still 6 on both sides. Conservation of mass equation is balanced, or the reaction is balanced. Okay? All right. For a single reaction, how many molecules of each substance would be consumed or produced? So, nitrogen, we're talking about molecules now, individual molecules in a single reaction. Molecules, we have 1 of nitrogen, 3 hydrogens, producing 2. So it is a 1 to 3 to 2 ratio. If the reaction occurred 100 times, how many molecules would be consumed or produced? Well, if this occurred 100 times, I would need 100 nitrogens to react with 300 hydrogen molecules to produce 200 of the ammonia. It's still a 1 to 3 to 2 ratio. If this occurred 538 times, how many molecules would be consumed to produce? Well, I would need 538 nitrogen molecules. I would need 3 times 538, and I would need 2 times 538. These are still in a 1 to 3 to 2 ratio. And I bet you could probably guess, if I added on here, what if the reaction occurred 6.022 times 10 to the 23rd times, which is a mole, by the way. What if it occurred that many times? Then I would need 1 times 6.022 times 10 to the 23rd molecules of nitrogen. I would need 3 times 6.022 times 10 to the 23rd molecules of hydrogen, and I would need 2 times 6.022 times 10 to the 23rd of these. By the way, I'm not going to write 6.022 times 10 to the 23rd. What if I just said I would need 1 mole? I would need 3 moles. And I would need 2 moles, because that's what that number is. A mole is just a number. 2 moles. Notice it's still a 1 to 3 to 2 ratio. So these coefficients up here, I'm probably answering some of the questions that we're going to get to. These coefficients right here, they can refer to individual molecules, 1, 3, and 2, or they can refer to number of moles of molecules, 1, 3, and 2. Okay? How do the reduced ratios in the last column compare to the coefficients in the reaction? They are exactly the same. Use mathematical concepts to explain how your answer in part A is possible. Well, the particles always react in the same ratio. Because you have to create the same ratio in order to have this particular reaction always occur. Otherwise, you're going to have a different reaction, different ratio, different coefficients. Even 538 is a small number of molecules to use in a reaction. Typically, chemists use much larger molecules, as we've mentioned before, like 6.02 times 10 to the 23rd. Remember, that's a mole. Consider each situation below as it relates to the reaction in Model 1. Same reaction, same coefficients, but now we're looking at, I kind of already did this for you, if it occurred that many times, which is just a mole, then we would have 1 mole of particles here. We would have to have 3 moles of particles here. We'd have to have 2 moles here, and it's still a 1 to 3 to 2 ratio. This number right here is just a mole. How many moles? I just said it right there. I already answered that question. All right? Refer to the data table in question 4. Right here. How do the reduced ratios in the last column compare to the coefficients of the reaction? Exactly the same. So as mentioned, these coefficients, they can refer to actual molecules or the number of moles of molecules. That's what those coefficients are talking about. I am going to start saying moles in reference to those coefficients. Those coefficients now to me are always going to mean how many moles are reaction, in what ratio, as far as molar ratios, are the molecules are reacting in this in these equations, or these reactions. The ratio obtained from the coefficients in the balance equation is called the mole ratio. What is the mole ratio for the reaction in Model 1? It is a 1 to 3 to 2 ratio. Now, all three of those, here are your two reactants, here's the product. You could compare any two if you want to. You could say the two reactants are in a 1 to 3 ratio. The first reactant and the product is in a 1 to 2 ratio. The second reactant and the product is in a 3 to 2 ratio. Okay, so you can compare anything you want to, or you can say all three. This is a mole ratio because you're comparing how many moles react and are produced. Okay? We're basically comparing number of particles, and moles is just how many particles. It's a large number of particles, but it's a certain number of particles. It's just a number. Use the mole ratio from the balanced chemical equation in Model 1 to solve the following problems. We're going to set up proportions. So, how many moles of nitrogen would be needed to make 10 moles of ammonia? Well, here's what we're going to do. We need 1 mole of nitrogen to react with 3 moles of hydrogen to make 2 moles of ammonia. Okay? These are always reacting in a 1 to 3 to 2 ratio. So, this is saying, what if you had 10 moles of ammonia? What if, instead of just 2, you created 10? Well, all of these coefficients have to stay in the same ratio for this particular reaction. So if this number of moles of ammonia all of a sudden becomes 10, it just got multiplied by 5. That means these would have to get multiplied by 5 as well in order to keep the reaction in the same ratio. And I would have to have 5 moles of nitrogen, 15 of hydrogen to produce 10 moles of ammonia. If you want to use a proportion, you certainly can. You can say 1 to 3 to 2 or 3 to 2. 3 to 2 is equal to what to 10? And you can cross multiply and solve for that. Okay? Or you can just think about it. What multiplier, what factor did this increase by? Then these have to increase by the same factor. How many moles of ammonia could be made by completely reacting 9 moles of hydrogen? So this time I'm going to just play out with the proportions here, or the ratios. If you've got 9, just to show you another way to do this, 9 moles of hydrogen, and I want to find out how many moles of ammonia I need, or are going to be produced. Okay? I look up here at the mole ratios, 1 to 3 to 2, and I am curious to find the ratio between hydrogen and ammonia. Hydrogen and ammonia, it's a 3 to 2. Every 3 moles of hydrogen is going to produce 2 moles of ammonia. Well, I've got 9. That's triple. So you can already see where this is going, but I'm just going to show you how mathematically you can do this in case it gets a little more complicated. I'm going to multiply by a ratio, and I want to get rid of moles of hydrogen. So moles of hydrogen are going to go in the denominator, and I want to find out how many moles of ammonia I am going to produce. And I fill in the mole ratio using these coefficients. I produce 2 moles of ammonia for every 3 moles of hydrogen. Now I'm just going to multiply straight across, or I'm going to multiply by 2/3 basically. So I know that 9 moles of hydrogen, if I cancel those units, moles of hydrogen, times 2/3, multiplied by 2 divided by 3, is going to give me 6 moles of ammonia, and that's how I can find out using this ratio, using the molar ratio of this reactant and this product to find out how much product I'm going to have with 9 moles of hydrogen. By the way, whatever you're starting with, if you're starting with moles of hydrogen, that's going to go in the denominator, and whatever you want to get to, whatever you want to find, that's going to go in the numerator when you set up these molar ratios. Okay? And then you just multiply to find your answer here, in this case 6. How many moles of hydrogen would be needed to react completely with 7.41 moles of nitrogen? Now they're throwing in 7.41 because it's not as easy. Before we had 9, 10. It was easy to see, what factors were being used, but 7.41. So let's use our mole ratio now. How many moles of hydrogen would we need to completely react with nitrogen? Okay, so we've got 7.41 moles of nitrogen. Write that down, what is given. Now I want to set up a mole ratio. I am going from moles of nitrogen, so that goes in the denominator, and I want to find moles of hydrogen. That goes in the numerator. I just fill in now the coefficients to find my mole ratio. How many moles of hydrogen react with how many moles of nitrogen? It is a 3-to-1 ratio. So that tells me I multiply by 3/1, and that's going to give me my number of moles of hydrogen. So on your calculator, you can take 3 times 7.41 and get your value there. Consider this situation as it relates to the reaction in Model 1. Nitrogen, hydrogen, ammonia again, same reaction. Calculate the amounts of reactants consumed and the amount of product made. Record the mass ratio of each of these. Okay? Now they're asking us how many grams of each substance would be consumed or produced in the situation in question 4. Let's go back up to question 4. Question 4 is saying a mole, 3 moles, 2 moles, assuming those coefficients are representing moles. So if we have, now we want to find out what is the mass. So 1 mole, and we're going to have 3 moles, 2 moles, but the mass quantities are different because a mole of nitrogen has a particular mass. What is the mass of a mole of nitrogen? We have to look at the periodic table. Remember, the molar mass you find straight from the periodic table. Here's nitrogen, 14. But it's not just nitrogen, it's N2. So N2 is going to have a molar mass of 28. So if you have 1 mole times 28 grams per mole, that means a mole of nitrogen has a mass of 28 grams. Hydrogen, 3 moles of hydrogen. Each mole of hydrogen, because it's H2, H alone has a molar mass of 1. But since it's H2, H2 has a molar mass, a formula unit or formula mass or a molar mass of 2. So I multiply this by 2 grams per mole, and I'm going to end up getting 6 grams is the mass of 3 moles of H2. 2 moles of NH3, well, NH3, 1 N is 14, and then 3 H's, 3 times 1, that's going to give me 17. So I have to multiply this by 17 grams per mole. That's going to give me 34. So these are always going to react, these 3 in this particular reaction. If you look at the masses now, this is mass, not moles. The mole is always reacting in 1 to 3 to 2. But mass quantities are always going to be in a ratio of 28 to 6 to 34. Okay, or if you want to reduce that, you could reduce that and divide everything by 2. So 14 to 3 to 17. Not the same as the mole ratios. Completely different, because we're talking about masses now. Alright, the point here is, can the mole ratio from the balanced equation be interpreted as a ratio of masses? No, this is not the 1 to 3 to 2 ratio. This one is for moles, and these are your coefficients. 14 to 3 to 17, that's mass. That is nowhere, these numbers are nowhere on the balanced chemical equation. Never will be for mass. So you have to realize that the balanced equation, those coefficients are giving you the molar ratios. Okay? Alright. Can the mole ratio from a balanced equation be interpreted as a ratio of masses? Oh, just answered that. The point here is that yes, I use the mole ratios in order to come up with the masses and look at the mass ratio, but I don't want you to be confused here. I always want you to realize that the coefficients in a balanced equation is giving you the molar ratios, not the mass ratios. Okay? So that's what I want you to understand there. Okay, remember that the mole ratio cannot be used directly in this situation. Note, you do not need to do the actual calculation here. Okay, what mass of nitrogen is needed to produce 30 grams of ammonia? Well, yes, that's true, the mole ratio cannot be used directly, but we would convert each of these to moles. That would be my suggestion. Yes, we could, if we wanted to, we could use, now that we have them, the mass ratios, but how did we get those mass ratios? We had to convert moles to mass. Okay, we had to convert moles to mass, moles to mass. So here would be my suggestion for you. And I'm going to set this up, I'm going to set up a table, and I'm going to show you exactly how you can get everything you need when you're dealing with moles and masses in a balanced equation. So let's take our nitrogen, 1 mole of nitrogen plus 3 of hydrogen, producing 2 of ammonia. Okay? And I'm going to write down a little table here below. And I'm just going to show you how you can get everything you need when dealing with these types of problems. Okay? So the first thing I'm going to just write down is, I'm going to write down in this first row, I'm going to write down the moles. And I'm just going to get that straight from the coefficients. 1, 3, and 2. Then I'm going to put here the molar mass. Where am I going to get the molar mass? I'm going to get that from the periodic table. And then I'm going to put mass here. Okay? Molar mass for nitrogen. Each nitrogen has a molar mass of 14. There are 2 in this molecule, so this is 28 grams per mole. Hydrogen has a molar mass, H2 has a molar mass of 2. Hydrogen has a molar mass of 1, but it's H2, so 2 grams per mole. Okay? NH3 has a molar mass, nitrogen and 3 hydrogens, that's 14 plus 3, that's 17 grams per mole. Okay? And then I just take 1 times 28 would give me the mass here that I have, 3 times 2 would give me the mass that I have here, and 2 times 17 would give me the mass that I have here. Okay? So this would give me 28 grams. This would give me 6 grams. This would give me 34 grams. Now, here's the deal. In any one of, in this table here, let's say that you were given a particular mass of nitrogen. Okay? Not 28 grams of nitrogen, but a different mass of nitrogen. Okay? Well, all you do is you do exactly the same calculations that I did. So for example, if you're given this mass down here, it's not 28 anymore, it's some other value. And you want to find out how many moles that is, well, you would then go the opposite direction and you'd have to divide by 28 grams per mole to find out how many moles that is. And then if you want to find out how many moles of hydrogen you need, you use this ratio, the 1:3 ratio. And then if you want to find out how many moles you have of hydrogen, you would then multiply by the molar mass. Okay? If you want to find out how many moles of ammonia are produced, you would then use the 3:2 ratio. And then if you want to find out how much mass that is, you would multiply by the molar mass of ammonia. So every time you go up or down in this column, you have to use the molar mass. If you know the moles and you want to find the mass, you multiply by the molar mass. If you know the mass and you want to find the moles, you divide by the molar mass. If you want to find out how many moles of something else, if you want to jump over this bridge here, you've got to use the mole ratios, 3:1 or 2:3. Or if you go in the other direction, it's a 3:2 ratio. Okay? So moving up and down this column, you use the molar mass, either multiply or divide. Going across the column, you're going to multiply by the molar ratios. And you always, whichever one you're going to, that's the top part of your ratio. Whichever one you're coming from is the bottom. So if I want to go from nitrogen, moles of nitrogen, to moles of hydrogen, I would multiply by 3/1. If I want to go from moles of nitrogen to moles of ammonia, I would multiply by 2/1. If I want to find out the moles of ammonia given the moles of hydrogen, I would multiply by 2. The one I'm going to, 2/3, the one that I have. Okay, we're going to be doing more of this in a little bit. So let's look at Model 2. Model 2 has proposed calculations for the mass of ammonia and to the mass of nitrogen. So let's look at three people's method, and then we're going to kind of critique it and see if we can find out how we can maybe come up with a method of our own. Three proposed calculations to solve the problem in question 10. We'll look at that. Complete the calculations in Model 2 by filling in the underlined values. Which method does not use the mole ratio in an appropriate manner? And two of the methods give the same answer. Show that they are mathematically equivalent methods. All right. So the question here is, what mass of nitrogen is needed to produce 30 grams of ammonia? So I kind of already set up a method of my own. But let's see what happens down here in the students' methods. Mass of nitrogen. By the way, this is the way I would attack it. Okay, I've set up my balanced equation, and I've got moles, molar mass, mm, and mass. Okay, and I am asked what mass of nitrogen is needed to produce 30 grams of ammonia. I am given mass of ammonia. I'm given this number right here. Okay? What do I want? I want to find the mass of nitrogen. I want to know what this number is over here. You can't go straight there. You can't go straight from 30 grams to the mass of nitrogen. You have to always go from one column to the next. You always have to use the coefficients, the mole ratios. So I need to go from mass to moles, and then this number of moles all the way over to this number of moles, and then from moles to mass. It's going to take 3 steps. Okay? So to go from mass to moles, I need the molar mass of ammonia, which is 17 grams per mole. If that's the mass for 1 mole and I have 30, I'm going to take 30 and divide by 17. Okay? 30 grams divided by 17. It's almost 2 moles, right? 34 would be 2 moles. So I've got almost 2 moles. So 30 divided by 17. Then I'm going to take this number and I have to come over here to how many moles of nitrogen would I need then? Well, nitrogen and ammonia react in a 1 to 2. If you've got 2 moles of nitrogen, you only need 2 moles of ammonia, you only need 1 of nitrogen. You need half as much nitrogen. So whatever number this is, 30 divided by 17, I need half of that, 1 to 2 ratio. So then I would multiply by 1/2. That gives me my 30. I'm keeping these numbers because I want to show you the calculations. 30 divided by 17 and then multiplied by 1/2. Okay? Then I want to find out what mass that is. I have to then multiply by the molar mass of nitrogen, which is 28. So I'm going to multiply by 28. So we did 30 and we divided by the molar mass, and then we multiplied by the mole ratio, 1 to 2, and then we are going to multiply by the molar mass of nitrogen. This 17 is the molar mass of ammonia, this is the molar mass of nitrogen, and that would give us our answer. So you have to feel comfortable. This table really helps me because I just move around this table and I know anytime I'm going up or down a particular column, I'm using molar mass. Anytime I'm going from one column to another, I have to use the mole ratios. And I can be given any value on this table and I can find any other value on this table that I need. Okay? So let's see which student did this particular method or similar setup. Okay? So here, all right, so this one here, you can see right away, they are setting up a ratio of grams masses and equating it to the ratio of moles. Can't do it. These coefficients are mole ratios, they are not mass ratios. That is the problem with this one. All right? Rachel took our 30 grams and she is going to divide by 17. Great, that gives her the moles of ammonia. Then she's using her mole ratio. She knows that nitrogen and ammonia react in a 1 to 2 ratio. She's setting up another proportion, which basically is what we did. So she's going to take this mole of nitrogen right here. She's going to put that number in there and now solve for X. That's going to give us moles of nitrogen. That's what we did when we went from third column to first column. And then she's taking the moles of nitrogen to find out how many grams that is. She's multiplying by the molar mass of nitrogen, and this is fantastic. Here is first step, going from given mass up the column. We have to divide by the molar mass. Then if you go from column to column, you have to use the ratio. So here we're going from column 3 moles over to column 1 moles. We multiply by the molar ratio of 1/2. And then to go down this column, we have to go from moles to mass by multiplying by the molar mass. And that's what happens right here to get our correct answer. Fantastic. Okay? Jerry sets it up exactly the same way. He just writes it all out in one step. So we have mass of ammonia dividing by the molar mass. That gives us, if we stopped right here, that would give us the moles of ammonia. Then we multiply by the mole ratio, that is from the coefficients of the balanced equation. This, if we stopped right here, this would give us moles of ammonia. And then we multiply by the molar mass of ammonia to give us mass in grams of ammonia. You always know this method here, you always know the steps because you can look at what you have, and what you have goes in the denominator, what you want to find goes in the numerator. Then put in the correct numbers. So I'm going from mass of ammonia, that cancels, to moles of ammonia. Now this cancels, I go to moles of nitrogen, then this cancels, and I end up with mass of nitrogen. Okay? So I think we took care of all of that. And we did this already. Okay, we took care of that. And these calculations will give you exactly what you need there to find out the, oh, sorry, this is for hydrogen now. Now they're asking us for hydrogen. Okay, I'm going to set up my table. I have a preference here. I'm biased, obviously. So if I do this, N2 plus 3H2, you can use Jerry's method if you want to, or you can use Rachel's method if you want to. I'm going to set up a table, and then you can use my method if you want to. Okay? So we've got moles, molar mass, and mass. So I know that when I do this, I've got 30 grams of ammonia. I'm given this value right here. I cannot go straight to mass of hydrogen, which is what I want. I've got to go up here, and then I have to go over using mole ratios, and then I'm going to go down. So 30 grams, I want to go to find out how many moles that is. So I'm going to divide by 17, because it's 17 grams for each mole. 30 divided by 17. Then I'm going to multiply by my ratio. This time I'm going to hydrogen coming from ammonia. So I'm going to multiply by 3/2. So 30 17ths, I'm going to multiply by my mole ratio of 3/2. And then I'm going to multiply by the molar ratio of hydrogen, which is 2 grams per mole. And so it's going to be 30 17ths times the mole ratio, and then I'm going to multiply by 2. So if you want to write that all out using Jerry's method, it looks like this. 30 grams, and then I'm going to multiply by 1/17, because that's grams to moles. This is for NH3. Then I'm going to go and use my mole ratio, and I have 3 moles of hydrogen for every 2 moles of ammonia. And then I'm going to use my molar mass for hydrogen, and that is 2 grams for every 1 mole of hydrogen. So look what happens here. Grams of ammonia cancel, moles of ammonia cancel, moles of hydrogen cancel, and if you do this, 30 divided by 17 times 3 divided by 2 times 2, you are going to get the grams of hydrogen needed in this reaction to produce 30 grams of ammonia. Cool, huh? That's fantastic. All right, extension questions. 1 mole of any gas will occupy 22.4 liters of volume at standard temperature and pressure. By the way, standard temperature and pressure, STP, standard temperature, I believe, is 0 degrees Celsius. Pressure is 1 atmosphere. Okay? Consider the situation as it relates to the reaction in Model 1. Calculate the volumes. Now we're talking about volumes. These are gases. And if a gas is going to occupy a specific volume at a given temperature and pressure, then we can use volume instead of moles. That's what they're going to get to here. Okay, so for gases, volume, every gas is going to occupy the same volume given the same temperature and pressure, and that is going to be also telling you that you have the same number of particles. Okay? So, how many liters of each substance would be consumed or produced if the reaction occurred a mole number of times? So, if you've got 1 mole of nitrogen reacting with 3 moles of hydrogen, producing 2 moles of ammonia, and if you have a mole of gas and it occupies 22.4 liters, then you would take 1 times 22.4, so this would be 22.4 liters. This would be 3 times 22.4. Okay, so that's going to be 67.2, I believe. Okay, 2 times 22.4, so that's 44.8 liters. But it's still a 1 to 3 to 2. This is a 1 to 3 to 2. So volume or number of moles can be interchangeable when you're talking about gases. This is only for gases. Okay, and as long as you're at the same temperature and pressure for all of the gases in the reaction. So it is always going to be a 1 to 3 to 2 ratio. All right. Can the mole ratio from a balanced equation be interpreted as ratio volumes for gases? Yes, it can, because of that condition. A mole of any gas is always going to occupy the same volume. Okay? And I just explained that in words right there. 1 mole of any gas occupies same volume. You can't do that with masses because the masses are different for every compound, element, whatever. Explain why the ratio of volumes is not followed in the following reactions. Well, you can't do it if you've got liquids. You can't do it if you've got solids. It's that simple. It only works if you've got all gases. All gases. Okay? Which of the following quantities are conserved? Meaning, before and after the reaction, you have the same amount. In the chemical reaction, find an example or counterexample from this activity to support your answer. Molecules, yes, they have to be conserved. You have to have the same number of particles before and after, and therefore moles as well. Yes, you'd have to have the same number of moles before and after, because moles is just a measurement of number of particles. Mass, since you have the same number of particles before and after, they don't lose or gain mass, so you have to have mass of conservation. Yes, that is conserved. Volume, no. Volume is not going to necessarily be conserved because you might have solids, liquids, so you might create a gas from a solid. Gases are going to spread out. Those particles have more energy. They're going to spread out and occupy more volume. So that is not always going to be the case. Okay? Unless you're talking about a reaction with all gases. If they're all gases, then volume could be conserved. Atoms of an element. Atoms of an element, yes, that is true. Okay? Oh, you know what? I need to make a correction up here. Where it says molecules, I apologize. I was thinking that that was atoms here. Molecules are not conserved. So for example, if you've got water as a reactant, that doesn't mean you have to have water over here as a product. No, I apologize for that. Molecules here are not conserved. It is the atoms of an element that are conserved. You have to have the same number of nitrogens on one side as you have on the other side. But just because you have N2 on one side doesn't mean you have to have N2 on the other side. Those bonds are broken and new bonds are formed. You're going to have a different compound that has nitrogen in it, but not the same molecule. Okay? So not molecules, but definitely atoms. Okay? All right. I hope that is very helpful. And this is an important topic when we're talking about moles and mole ratios in reactions, because we're going to be using this as we're talking about calculating masses and moles in a balanced equation. I've shown it to you right here. Okay, what we did actually is called stoichiometry. We're using the mole ratios in order to calculate how much is produced or how much is consumed in a given reaction. All right, great job, and we will see you in the next video as we continue our talk in chemistry.